Thank you, Anima. All yours. Thank you very much once again.
Thank you, Ayush, and great to see all of you at CMU. And I have nice memories of visiting the place. I've always been so energized by all the machine learning research happening there. And most recently, my former student is now postdoc Farooq Arabshahi with Tom Mitchell there, and she tells me of all the cool things that are continuing there. So it's my pleasure and privilege to give this seminar. So today I'll talk about, where we are with deep learning. It's been a lot of excitement, but also we're seeing severe gaps, right, when it comes to what AI can do today versus the human intelligence, which is the ultimate goal. I'll try to avoid the term AGI because it's just been so overused and so hyped up. But what I want to ask is more at the core of it, what are some inspiration we can get from biological processes happening in our own brains and how to build some of that into AI methods, right? I mean, we're not going to be focusing on biological plausibility, which says, we have to be accurately modeling what happens in the human brain. Instead, we'll use that as an inspiration and see how to maybe mimic some of those outcomes in AI. And feedback and compositionality to me are at the core of this human intelligence. And I'll give you some overview from neuroscience and how we can build it into artificial networks. So that's the plan for this talk. And as always, feel free to interrupt me, or maybe it's efficient to have that in the chat messages, and maybe Ayush, you can interrupt me if there is something that's very pertinent so that we can clear up immediately rather than wait till the end. Awesome. Sometimes I have to stop and start sharing again. It just gets stuck once in a while. Give me a second. This tends to happen. Okay, is this, yeah, this is working now. Great, so, we all know that humans have such amazing abilities for few shot or even zero shot learning, right? For instance, a child that has never seen a dolphin would still understand that it is some kind of an aquatic animal, right? It's able to swim, it has eyes, it's able to see us, it's able to interact with us. Whereas an AI method currently would have severe trouble trying to reason about what this dolphin is if it's never seen an example of dolphin in training data. And that's where I think that few shot and zero shot generalization in humans is so hard to get for AI. And one question is even how to design good benchmarks to assess such abilities, right? Abilities of humans being able to do this very easily, but really hard for current AI methods that overfit to training data to be able to do well. So that's something I'll address head on in terms of how to have good benchmarks to test this few shot generalization. So this is an impressive ability. So let me see again. I think because this is not, okay, now it's in the foreground. Yeah, so the other ability is robustness, the ability to just handle all kinds of corruptions, right? So this is the famous ImageNet-C example. And for us humans, we have no trouble seeing that it's a bird in all these different levels of noise, different kinds of noise. But if a neural network has never seen this during training, it is going to have almost an impossible time to accurately say what's in an image. And so this is...
Sorry to interrupt you. Some people are saying that they're still seeing the title slide.
Okay, I guess I can stop sharing and start sharing again.
Chris,
I don't know.
Is it just with you or is it with other
Can you see it now?
I see it now. Thank you.
Okay, everyone
great.
good? Okay.
Yeah.
Yeah, so we talked about zero-shot generalization, we talked about robustness, and then now we can talk about creativity of humans, right? Our ability to create new music or art or any kinds of new works that's never seen before, right? Is points at compositionality. You know, we are able to grasp certain concepts and make entirely new samples based on that grounded concepts or symbols. So how to enable such compositionality seamlessly in AI as well. And if you look at the current AI methods, they're mostly not compositional, right? So if we take our standard networks for computer vision or NLP, they just are a black box. I mean, there is a network, you feed in the training data, you try to optimize for accuracy or similar such metrics. And so if we have to create something entirely new beyond the training data or handle something beyond the training data, it doesn't have this compositionality. And so what are some principles to enable that? And how to test for compositionality in a very principled manner. I think this is the other aspect we want to address. And as I said, a lot of inspiration comes from human intelligence and in fact from babies and children, right? So at a very young age, we can do such impressive learning that's far beyond the capabilities of current AI methods. And it's known that infants predominantly do unsupervised learning. So unlike our popular deep learning methods that are mostly supervised, most of infant learning is unsupervised, right? So, and I think that also points that the next revolution in AI should be unsupervised. How to deal with limited or no supervision, how to disentangle different kinds of concepts, and how to be able to do different skills, different task inference in robotics, for instance, and how to have causality in our reasoning in AI, right? So that helps us also to extrapolate to new instances because we know the underlying cause and effect. I think these aspects we need to bring into AI and have the inspiration from how babies learn. I think that's an exciting avenue. And just to kind of lay out this foundation, I want to quickly point out where current deep learning is and what should be the new foundation for AI that is generalizable. And so for this, I would like to break down the AI method, any AI algorithm, into three parts, right? How it deals with data, what kind of data is it going to work on, and what kind of priors is it going to incorporate? And how do you design the task? So what kind of metrics are we using to assess the task and the action, right? So if there is an interactive environment, such as in reinforcement learning, there's also action in terms of some decisions to be made. And so this combination is an AI algorithm, right? And in some special instances, if it's only passive learning, there is no action, there's no interaction, right? So then that's a special case, but this is the most general framework. And so given this, if we look at where deep learning is today, it's mostly data hungry because we are going towards bigger and bigger models that require even more massive data sets. And most of them are supervised learning methods that require extremely expensive human labeling, right? So this becomes untenable. Or they make use of very simple priors. So if it's computer vision, we know we can use convolution, right? But that's such a simple prior, and we are not using much more domain-specific or robust priors. And this is an aspect that I'll address, how feedback can be a great prior for enforcing in neural networks. But at the moment, because we don't have robust priors, it's very brittle, right? I mean, these famous examples of if on the stop sign, you just put a few blocks that are strategically placed, it can completely change the classification of this stop sign, shows the danger and the vulnerability of current methods and how it's not ready to be put into safety critical applications like autonomous driving. So the use of priors, I think we are very weak at the moment with standard deep learning methods. And so the question is, for domain specificity, can we use much better priors? And also for domain agnostic setting, for just general, say computer vision, are there better priors like feedback? So that's another aspect. The third one comes to the design of the task itself. And I think this aspect is also something we need to really think again, because it's not just one of leading to bad algorithms and bad performance, but it can have also huge societal implications, right? So if you follow me on Twitter, just over the last few days, we've been talking about the racist and sexist AI cropping on Twitter. I mean, of course, we don't know what is internally being done there, but from what's externally published by Twitter, they say that there is saliency, that they record the eye gaze, and based on that, they try to come up with intelligent ways to crop pictures when somebody uploads on Twitter. But the question is, who was in that training data set? Most likely, it is going to be straight white male, right, in like the, so that's not representative of everybody else. And so their gaze is now being co-opted at a massive scale by all of us, and we have no option because that's what Twitter decides to do. So that shows that the way we collect data, the way we design benchmarks, the way we test it can lead to a huge amplification of racism, sexism, and other biases that are present in our current society. And this famous example that started this field of AI ethics is face recognition, right? And it's now well known that publicly available APIs, such as the Amazon face recognition API, is heavily biased against dark skin tones, and especially women with dark skin tones. So this shows that the way we design tasks at the moment as a leaderboard chasing culture of fixed training data set, fixed test data set, right? I mean, that only encourages us to do well in that narrow way and not in a broad generalizable way in terms of what happens at the so-called corner cases, right? So, those that are not white male are not corner cases in the real world, but in these data sets, they become the corner cases. So I think it's extremely critical for us to design better generalizable AI to overcome these kind of bias issues. So that's something I always make sure to highlight in any talk I give, because it's not just about the performance. We need to think about the broader impact of the methods we're all designing, and we're all responsible for this current bias amplification. So that's where we are today. The question is, where do we head next? What are some new frontiers on each of these facets for designing an AI method? So when it comes to data, as I said, the next revolution is unsupervised, and we've already seen some exciting developments with self-supervised learning methods, right? So what we want to further hone in here is in terms of how can we learn new concepts better? How can we disentangle different factors of variations? What can we do with limited amounts of supervision? Or how to come up with good transformations for self-supervised learning methods so that we get good representations. I think this bucket is so important for us to move beyond standard supervised learning. And I believe that by also moving away from tasks designed for supervision, we can also minimize the effect of societal bias, right? Because then we are not just optimizing for one metric. So that's something to think more about, how we can design a whole range of different measures based on unsupervised learning rather than one fixed measure. And that relates to also having multiple tasks and domains rather than being learning on only one fixed data set. And then when it comes to priors, as I mentioned, we need to create more robust priors. We want to ask how to use domain knowledge. We want to look at feedback as an example of structural priors, how to create more inherent robustness in our current networks. And then with the task design, it would be great to make it as adaptive and those that discourage overfitting, because everything you see right now is mostly designed for big models to win, right? Even the GPT-3, I mean, they can call it zero-shot generalization, but that's just a sham, right? That is just complete nonsense. It's just looking at the context, it's completely overfitting and memorizing. So there's a lot of marketing hype, which annoys me a lot when it comes to how big companies are just misusing terms. So we are nowhere near good zero-shot generalization. And so that means we have to carefully design tasks, then benchmarks that can honestly test methods for this ability to generalize to new unseen scenarios. So that's where I'd like to see the next frontier, make the learning unsupervised, have robust priors, and design adaptive tasks that discourage memorization and overfitting. So given this, what are some recent advances that my group, both at NVIDIA and Caltech, have done, and how do we kind of get to this next frontier? That's what I want to use the rest of my talk to go deeper into. But are there any comments and questions before we dive deep into those?
You can raise your hand if you have any comment or question. I think we are good for now. Yeah.
Great. Awesome. So now, so today I will not go into the details of how to use domain knowledge to design robust priors, right? For instance, if we are looking at landing drones, we don't want to learn from scratch, right? We already know Newton's laws of motion. So how to use existing controllers and augment that with AI rather than learning from scratch is the natural question. And so a lot of other works that we've done looks at using such domain knowledge or using structures like tensors and graphs or simulations that are available to use as a prior, right? And that's something that we need to go much deeper into in terms of not just use a black box standard neural network, but something that is specifically designed for this task and domain. But I won't go into more in this talk here. So given this, the first aspect I want to cover is what are some known biological mechanisms for generalization and robustness. So these slides are thanks to Doris Au, who is my collaborator at Caltech and neuroscientist, right? So she helpfully gave me this background on what are some exciting new experiments people are doing in neuroscience to uncover this source of robustness and generalization, which is through the feedback mechanisms in the brain. So the idea is when we are seeing an image, right, it goes through the retina, then it goes through the visual cortex, and then ultimately IT cortex, right? So it goes through these hierarchical layers, and this is the feed forward step. But the cool thing is it's not just feed forward. After some point of time, there's also feedback. So you go now top down from the IT cortex all the way to V1, which is the first visual cortex layer or the primary visual cortex layer. And so that's what's missing in the current artificial neural networks, right? We mimic the feed forward mechanism of going from lower layers to higher layers, but we don't have the concept of top down or feedback that feeds the signal back from the IT cortex all the way down. And there have been lots of interesting experiments to uncover what this feedback is doing, what feedback is responsible for in the brain. For instance, in this piece of work, it's looking at what are the distinct modes of vision that is offered either by feed forward or recurrent. So feedback is also called recurrent because that happens multiple times, right? It's not just one shot, but there are many iterations of feedback. And so that's why the term also recurrent processing. And what this example shows is if you can have a mask stimulus, so essentially you're like masking the effect of feedback, right? You're preventing this feedback from happening in a top-down way. When that happens in this experiment here in this paper, what they saw was, in some cases, you may not even see any image. The idea is without feedback, there is no perception, right? So in many cases, you may not even perceive that there is an image in front of you. And so that shows the critical importance of having feedback in our perception. And also there are experiments to show that to do figure and ground segregation, so meaning like there is the foreground and background here. So in order to do that, feedback is essential. And what this experiment shows is if you had a figure with no dot here, right? So there's only background, there is no foreground. It's much quicker for us to perceive what's in this image. On the other hand, if you have to do this segmentation between the foreground and background, it takes longer time, and that longer latency means a feedback is needed, right? Because the feedback only happens about, after around 100 milliseconds or so. So you have to wait for the feed-forward signal to propagate all the way to IT cortex, and then the feedback kicks in. So if you look at, at what point is the stimulus or the spiking activity happening in the brain, if you record this, for simple images with no foreground and background separation, it happens very quickly, right? Meaning feed forward is enough. But if you have to segment the foreground and the background, feedback appears to be essential. And so this shows that maybe that's why we are so good at being able to segregate figure and ground or foreground and background so effectively compared to artificial networks where segmentation of any out of domain or images that are not in training appear to be so much harder. So that's one example. Another example showed something similar. What it showed was if you have now an image with grating, so essentially there is again no foreground or background separation, or the one with the hole, so now you have to do segmentation, or rather the mouse has to do segmentation. What it shows is if you inactivate the feedback, you just can record that the mouse is not responding to the hole. So rather it's not able to perceive this separation between foreground and background. So what these experiments show is that feedback appears to be essential to predict the presence of an object, right? So there is almost no perception of this different objects in a scene if there is no feedback. And people have also tried to find ways to remove feedback. I think the first experiment I mentioned said if you mask the feedback, people don't even see images, right? And in another setup, what they did was if you ask people to make a decision very quickly, you want the participants to classify what's in the image within 100 milliseconds, because we know feedback only kicks in after 100 milliseconds. What they showed was extreme brittleness. In fact, about 67% of the participants wrongly classified the image. So whereas if you gave them enough time, it was almost 100%, right? So what this shows is if humans are not allowed to use feedback, they're almost as brittle as our current networks, right? Or even worse. So the source of brittleness in artificial networks can be related to the lack of feedback in those networks. So I think hopefully all these examples give you some sense of why, as a biological mechanism, feedback is so essential. And in fact, there are also theories that argue that feedback, in fact, may be important for our consciousness, right? Because without feedback, the information is not accessible for the entire brain. And without that access of information, you really cannot be conscious, because consciousness comes from that integration of information. And so if that's the theory we believe in, then we want to ask how feedback is now the source of consciousness in biological beings, including humans. So that shows that we have to carefully think about how to design it in our current artificial networks. And so there's also critical role of feedback in control theory, right? So if you're studying control theory like I do, at Caltech, we have so many experts in control theory, such as Baba Khasibi, Aaron Ames, Sunjo Chung, and through collaborations there, right, we are looking at ways to have efficient adaptive learning in control systems. So this is, again, something I won't go into detail here, but what is a primary tenet in control theory, right? So the idea is feedback means it's a closed loop, right? You're looking at how the system behaves. You're taking that feedback signal into the controller and changing how you control the plant or the system. And it's known that you need this closed loop or feedback to stabilize an unstable system. If you just had open loop, you cannot stabilize it, right? So instability, again, appears to be a core aspect of how the brain processes the external signals. Because unless you stabilize and minimize the error, you cannot get good perception. And so also from control theory, we know that in order to have an adaptive and reliable system, feedback is essential. You just cannot get that in an open loop system. And so all this points out to the need for designing feedback in our learning systems. And the most popular method to do this is known as predictive coding. So the whole idea is, if you take like some predictive estimator, let's say a neural network, a feed-forward neural network, and once you have this prediction, what you want is to have an error signal, right? Some way to look at what is the error between the prediction and the input, and further propagate that forward in recurrent steps. And so this is a very simple model. Usually it's done as an alternative to backpropagation, right? Because backprop is not biologically plausible. So can we instead have ways to locally propagate error signals and update the weights? But unfortunately, this mechanism, although biologically plausible, tends to have such poor performance on any of the standard networks, right? So it's barely getting to MNIST scale, whereas, we would like data sets, so rather methods that can at least scale to ImageNet's level. And so what we are seeing is this is a very reasonable first step to encode feedback, but then it's not enough to train networks from scratch, right? So the alternate approach, what we are using is to ask, can we propagate better error signals based on also learning certain generative modeling in addition to a predictive model? And can we still train with backprop? Because otherwise we can't get good efficient models, but use this error propagation mechanism only to do inference. And so test time, if you want to get to a good robust answer, we can use this error propagation. And so that's how we will proceed in the work that we've recently released that looks at adding this recurrent generative feedback into neural networks. So this is joint work between NVIDIA and Caltech. It's also interdisciplinary, as I mentioned. Doris Sau is a neuroscientist, so having that inspiration and background from neuroscience also made us much more excited about what it can do in artificial neural networks. Any questions so far before I dive deep into this?
Any question?
Hi, Anima. I had a question about the human feedback. So do we know how this human feedback is different from the backpropagation? Like, what are the features that human feedback is giving us extra?
Yeah, so what's currently known is it's more local, right? Usually you're not, like backprop requires end-to-end information of all the layers. And current, all the experiments point that that is unrealistic. So it's much more local between one layer and another, or maybe some limited top-down feedback all the way from layers that are far farther away.
Thank you.
Great. Any others? Great. So now diving into how we can build feedback that is going to help us with robustness, but also retains good, clean accuracy. That means on images without noise, it's still performing good. And what is some principled approach to adding the right feedback, right? Because, you know, I gave you an example before in predictive coding, you can define your error signal in so many different ways. But what is a principled way to bring that in? And also have incorporated generative priors to do the top-down feedback. Meaning the intuition is, in order to do top-down feedback, should it try to generate the input image it's seeing? How to incorporate that in an efficient way? I think that's the other principle we'd like to build in. So, and the main principle here is ultimately we want some kind of consistency, right? The intuition is, if you're doing many loops of feed forward and feedback, ultimately it has to converge to a point that is consistent. Meaning consistent in a sense that is the internal model of the world. You know, we all have certain internal model of how the world should look like, or in this example, how a cat should look like. And so this external stimuli of this cat coming in, right, should agree ultimately with what the internal model is saying, right? So if that happens, then you can confidently say that there is a cat in the image. And you can think of that as a process of denoising internally, right? So you're kind of taking in some external image, right, that gets processed, sent to the brain, to the visual cortex layers. And ultimately, there is some process of refinement happening because of the use of the internal generative model. And ultimately, we can come up with, we can perceive a sharper image of the cat and know it's a cat. And all this is happening in a subconscious way, right? So we are in effect hallucinating and trying to visualize a cat internally in our brain. So this aspect of self-consistency, I'd like to think of this as the ability to overcome all kinds of variations, right? You could see cats in different colors with different background, different blurriness and other noise. All these so-called nuisance variables don't ultimately impact that it is a cat. And that's happening because we are trying to overcome these nuisance variables. And so this we can frame mathematically as one of looking at the most likely configurations of each of the variables, right? So if X is my external input, so this is the image that we've seen, and it creates some internal representation. So think of this as the representation that reaches the brain. And ultimately, you want to come up with the label of what's in the image. And there's also certain nuisance variables, we'll call it Z. And so all these have to be agreeing with each other, right? So the idea is, what is the most likely label given these input features and nuisance variables? That should agree with what is the most likely reconstruction of the features given the label, right? So meaning internally, we should be able to hallucinate that it's a cat, given that we think it's a cat, right? So this consistency should be there amongst both the input, the labels, and the nuisance variables. And so that's how we can frame this mathematically, that this process of feedback should lead to a certain equilibrium point where consistency is met. Any questions here? I can't hear anything.
I think we are good for now.
Okay. Great. And
I think there's a question.
There is one question. Okay.
I think there's a question in the chat. If you, Atkinson.
Can somebody?
Oh,
Yeah.
Chris has a question. Let me read it. But the Chris is all. Chris, are you there?
I can read it.
Yeah.
You talked about things going to equilibrium, but the input isn't static. It isn't images, it's video. So why should the internal system go to equilibrium? If you have transient input, you really shouldn't expect steady states internally.
So at the moment, we are looking at just static images, right? So even with video, there is an external clock and the internal clock, right? The idea is, again, if you're keeping up with what's happening in the video, you should still have some locally consistent states because you have to perceive, oh, this is what's happening now in the video. Otherwise, you lose that, right? You don't know, you miss what's happening in the video unless you come to an equilibrium point before the video moves on. And we know in our brain, this feedback is happening much faster than usually the frame rate we see in videos externally.
Yeah, neurons are slow. They're on the tens or 100 millisecond time scale. So is video.
Right. I mean, so that's the question. Is it fast action ones or, you know, the ones we are perceiving, right? Usually they don't have fast actions. And if they do, then you have missed all the details, right? You're not able to do that careful perception of completely understanding what's in the image. And so in this talk, I'll only limit to images. So it's a good question of what aspects in what kinds of videos can we enforce this notion of consistency.
All right, thanks.
Yeah. Any others?
Any other question? No.
Great. So given this setup, now the next aspect is how to bring in some notion of generative modeling, right? And make it seamless with the predictive network. Because what we know is in the brain, the feed forward and the feedback together are using some form of generative priors. I think it's still a wide open question of what exactly is this generative model in the brain, but we all know there is certain internal model of based on all the representations we've seen in this world. So given this, what can we have in a, how can we augment any standard discriminative setup, such as say even simply a logistic regression with a generative model, right? So if you think of logistic regression by itself, there is no generative model, right? Because it only models the conditional distribution of the label given the input. So the input distribution could be anything. But then we can ask, under what setting, for what input distribution would logistic regression be the Bayesian inference? Meaning it'll satisfy the Bayes rule if you chose that in terms of the input distribution. And the answer is a Gaussian mixture model, right? So if you have the input as distributed as a mixture of Gaussians and the class label is the label Y, in that case, if you look at the conditional distribution of the label given the input, that reduces to a logistic regression. So in a way, you can reverse engineer and ask, what is a consistent input distribution that agrees with a chosen classifier? And we can ask the same question for a deep neural network. For any standard, say, new feed-forward neural network, we can ask the question, is there an input distribution for which this neural network is my chosen Bayesian inference, or is the correct Bayesian inference? So we can do the same. And the intuition is if you now have multiple layers in this neural network, what the right generative model should do is try to invert this, right? But this is just any arbitrary neural network, so it's not guaranteed to be invertible. So instead, what we can do is introduce hidden variables, and this you can think as the nuisance variables I initially mentioned, as a way to try to go from the label all the way to the input. And we call this a deconvolutional generative model. The idea is you can now try to invert going all the way from label to the input, right? And this intuition is in a way trying to manage the non-invertibility in the feed-forward process. So as a simple example, let's say these are ReLU units in this feed-forward process. Then in the feedback, you can think of these nuisance variables as Bernoulli distributed, right? Because in a way, what it's trying to predict is whether the feed-forward step had the ReLU gate to be on or off. So that's a Bernoulli variable. And then in the end, we can just add some Gaussian noise and take the limit because the Gaussianity will is again a simple parametric choice. We can also extend it to any adversarial choice of distribution here, but for simplicity, let's think of this as Gaussian. So any questions here?
No.
So what we are doing is in effect looking at a model that can invert what a feed-forward neural network does. And because of the non-invertibility, we have to introduce hidden variables, right? So what this also says is if we are now trying to incorporate a generative model into our given neural network, we also have to do unsupervised learning, right? Because these variables Z are hidden variables. We don't have supervision for that. And so what we in effect have to do is iterative inference that can jointly infer all these variables together. So in the first step, we can do the feed-forward process as before, right? This is the standard neural network, except now we have an additional hidden variables added here. And then in the feedback process, again, these we are going to update all in a top-down fashion, meaning we'll try to reconstruct the input given the label. And then we'll also try to update our latent variable inference. And we'll do all this together, right? So the idea is we'll alternate between feed-forward step, a feedback step, and updating of the hidden variables. And so this iterative inference now is a recurrent process. And this is our way of now building recurrent feedback into any given neural network. And so that's what we call it as neural network with feedback. I mean, we're now doing it with CNN, but you can do it with any other neural network as well, right? And the main process of this is now recurrent feedback in multiple steps. So doing feed-forward step, then the feedback step, updating hidden variables, and then redoing it again in multiple iterations. And so this is a seamless way now to add feedback to any given neural network. And so operationally, what this feedback is doing is now changing any kind of activations into adaptive activations, right? So if you have ReLU now, it's an adaptive ReLU, because now you're not just deciding what the ReLU should do based only on the feed-forward signal, right? The F is the feed-forward signal. But you also look at what is the feedback saying. And so you decide what the ReLU unit should be based on the feedback. And similarly for max pooling. So the idea is you're going to now adapt what the gating mechanism in the feed-forward step is based on the feedback process we are going to use. And the feedback process also utilizes the hidden variables that are updated. And so this is now this coupled both feed-forward and feedback process. And so you can see that the feed-forward step will update based on what the feedback says, right? And that's why it's no longer just a one-shot classification, but one that can now run in any number of loops. And so the main technical result here is, this specific design that we use to build the generative model. What that result says is that preserves the given feed-forward network we started with as the generative classifier, meaning we are able to do Bayesian inference in this generative model that is just reducing to doing the feed-forward process in the neural network, right? So once you can just do the feed-forward step and then take the feedback in, that's akin to doing Bayesian inference in this model. Any questions here?
Anima, I have a question. So let me put it this way. Can I apply this thing when a concept has never been seen before? I mean, it seems to me that right now what we are doing with the DGMs is basically applying some sort of feedback only at training time. And no,
this will also happen at test time. That's the key, right? So you can decide to do this iteration at any time, right? Because you don't need the training label to do this feedback.
So if I have, let's say my model was trained on all sorts of cats over there, and let's say a new species come in, dog comes in, right? So first, how would it know that it has not seen this kind of example before?
Right. So that's currently, so what we are doing is for robustness, right? So we haven't explicitly addressed generalization to a new concept in this current work, right? There are ways to extend it, but I agree, this currently doesn't address it, right? What it does is if you now give a noisy cat that was never seen before, it will try to denoise it into a known cat, right? So it is trying to project it back to the known image manifold, right? Or some image feature manifold.
I see. So in some sense, can I say, I mean, if I have to naively say it, let's say in PCA world, I'm trying to project it to the known eigenspace or eigenvectors over there.
And so what this is doing is it's doing it along the same path as the feed forward process, right? So it's a multi-layer, essentially denoising and projection steps. And you're also changing your label based on that projection, right? So it's now iteratively helping each other. So the idea is if in the beginning, you had like, you weren't sure it's a cat, right? Because it was very noisy. So you kind of have spread out your label into multiple classes. And then you try to do the feedback, right? So that also helps sharpen the confidence that it's a cat. So over the iterations, you're also hopefully getting a better label and also a better denoised representation of the cat.
I see. So right now the space of the labels is fixed, but if there was an adaptability where I can also add a new label, then I can extend this to new concepts, right?
Exactly. So you can extend this for lifelong learning, right? Because you can say, this is unlike anything I've seen before, right? Because even with all the feedback, I've tried to project it and it doesn't do a good job, right? And then that can help you create a new class, right? You can extend it in principle, this current method to that setting, but we haven't done that so far.
Yeah, got it.
Great. Any other questions here?
Anyone else? I think we are good for now.
Great. So, so just to, I didn't realize how much time went away. So yeah, the main kind of result was that this is a principled approach because we are building a generative classifier that agrees with the starting feed-forward network we chose in a Bayesian way. I mean, there are some technical assumptions. Mostly you want to like kind of have instance normalization and balanced label distribution. And this is also, we know, right, in practice, this also gives rise to good performance. So these are aspects we use in training. And the main idea is, in addition to cross entropy loss, right, with the target label during training, we can also add reconstruction loss in order to reconstruct some intermediate features of clean images. So if, for instance, during training, if you only see clean images, you can encourage construction to this clean manifold. On the other hand, if you also want to do adversarial training at training time, you can also encourage reconstruction to the clean counterpart of a noisy feature, right? So all this, you can, additional losses you can add in addition to the standard cross entropy loss. And so this is just a simple visualization on MNIST, given that MNIST is lower, sorry, it should have played for some reason. The idea is you can go denoise it all the way in the input space, right? So the idea is this is fairly low dimensional. We can reconstruct all the way to the input space, But for more challenging data sets, we will only reconstruct to some intermediate features and not generate the input, because that's not our ultimate goal. And so we can see that it has inherent robustness. So meaning this is standard training, it's never seen any noisy images during training time. And you can see that it can still hold up pretty well, right? Whereas a feed-forward network immediately collapses because it just can't handle any noise. So that's encouraging. And if you further, do many iterations of it, you get even further robustness. The idea is multiple feedback iteration leads to more robustness. And then ultimately, if you want to combine it with adversarial training, you get best of both the worlds, right? You get both good, clean accuracy as well as good adversarial accuracy, because we can augment both clean and noisy images during training and still hold up a lot of this. And in fact, the adversarial accuracy is higher than clean accuracy, which never happens in a standard network. This is because it has learned how to denoise these adversarial samples well, because it's seen so many of those during training, right? So this is an added benefit that we can be extremely robust to noise compared to standard neural networks. And that's kind of the summary of this line of work, showing how feedback can lead to good inherent robustness, and having adversarial samples or any corruption samples during training further enhances this robustness. And the core principle is having this recurrent feedback as thinking of it as iterative inference in a certain generative model, and having this generative model align with our chosen feed-forward neural network. So that way we can do efficient Bayesian inference, right? And so putting all this together helps us give rise to an efficient framework for handling robustness. So, I have 5 minutes. So in the remaining 5 minutes, I'll quickly introduce the other part of the talk that I wanted to give some intuitions on the compositionality aspect. So far what we did was more of a low-level robustness, right? The idea is you have all kinds of noise in the image. How can you handle it? And feedback helps us do it. But what about high-level concepts? We can compose different concepts so well together. And what we've shown in this latest work is a new benchmark that current big deep learning models just cannot cheat. I mean, you can build the biggest model, you can take the most sophisticated meta-learning method, and still the performance is very significantly worse than human-level performance. So we believe this challenge can be a good foundation for us to create better methods that focus on generalization and compositionality. And so this inspiration for this goes all the way back to the 60s. BONGARD created this challenge for humans, right? The idea is, some form of analogy testing, right? So we've all done puzzles like this. What is a common concept here in the set A that is not present in set B, right? For instance, we can say here there are like essentially two blobs or two objects connected together, but here there's only one continuous internal space, right? So these kinds of concepts we can intuitively figure out when we see images like this. And the question is, can we systematically create these kinds of objects using a programmatic approach and create lots of examples of this? Because BONGARD, I think, created only about 100 such puzzles, and that's not enough for our neural networks, right? That's too limited data to train big neural networks. So instead, we wanted to ask, is there a systematic way to create such tests for artificial neural networks? And what we thought of this as, right, few shot binary classification. So each example only has 6 positive and 6 negative examples. So each now task is entirely new. You don't know what is the concept that separates the set A from set B, right? So this is few shot learning, and you have many such problem instances. In our example, we have 12,000, but we can even further keep creating any number of such problem instances. And we've done like free form shapes, basic shape, abstract shapes, I think the details are not important, but what's important is we believe we can mimic some core properties of human cognition, right? And that's what we want to test in our artificial methods. The idea is it's not just pattern matching. If you take any standard computer vision task, it's likely to be just pattern matching, right? And we don't want that here. And that's why the same pattern can mean entirely different thing based on the context of other examples it's shown with. For instance, in this case, the property is having 4 straight lines, but in this case, the property is having 6 straight lines, right? So the same image can mean entirely different things based on the other images it is with. And we humans are able to have this kind of, right, flexibility in what the concept is by looking in context with other images. The other aspect is, right, like smaller concepts can compose to be bigger concepts. So here there are lots of circles here, but we know overall this is like a semicircle, right? So it's able to compose itself to a bigger concept. And then it's infinite vocabulary. So the way we programmatically generate means it's not a few fixed shapes. It can keep creating new shapes. And that's why you cannot overfit, right? You can't just fit to this limited vocabulary and say we can have this large transformer network and we are done. And so it prevents this overfitting and memorization, which I think is super important. And so these are some details of using this logo for procedural generation. But the main punchline is even the best meta-learning baselines perform very poorly compared to human abilities. And in fact, the expert human is nearly perfect in some of these tasks, whereas these are still far off. And the key thing is it's not even one method that wins all, right? For different kinds of tasks, different methods are winning. So this shows that we still don't have the answer when it comes to few shot learning. There's a lot of work, there's a lot of hype, but we are still very far from beating this benchmark. And that's why we are excited about this. So we can also use supervision of the actions that generated the image, and that does much better. So what this shows is if you do a neuro-symbolic approach, you have much better chance of winning this challenge, but it's still far away from human performance. So what this says is we have a long way to go when it comes to assessing compositionality in humans, of humans in artificial networks. And yeah, so to summarize this, which I went through very quickly, the idea is there is now a new challenge. I encourage you to go test it out, to create new methods that can do few shot learning and generalization very effectively. Thank you.
Thanks, Anima. Time for a few questions, depending on Anima's time. If you have a question, you can unmute yourself and ask. Okay, maybe I'll start meanwhile people are preparing their question. So Anima, one thing in the feedback, I have 2 questions, one from the feedback, another from the composition aspect. Feedback, in generally, most of the machine learning, we have this fixed data distribution, we learn something on it, right? Now, one of the big challenges is, I mean, if you think from a human perspective, we seek out for a feedback because we know that we certainly don't know some concept. But that's not true for the CNNs, of course. Like they make confident mistakes also, very confident mistakes. And so there is no provision so far that we can incorporate feedback nicely because they don't really know if they have seen that kind of data distribution. Now, wouldn't it be worthy that if we just have a system that tells that, have I seen this kind of data distribution earlier or not? If not, then isn't it better that we rather say, I don't know the answer to it, or I need some more feedback to learn about it rather than making a wild guess?
Right. No, I mean, precisely, right? So first of all, I think we sometimes oversell human intelligence. If you see current conversations in social media, it's not clear that there aren't a lot of overconfident, clueless people, right? So that's a cognitive bias we know, cognitive scientists have studied. So it's not always true that humans are always able to overcome the overconfidence issues and always have the right answer. But at least with, say, visual perception, in most cases, we are okay, right? So there's, I think, completely different kinds of cognitive bias even humans have. So that's one just quick comment. But yeah, when it comes to how to do this in artificial networks, what we've done in our feedback network is have the annealing process. So in the beginning, I have this temperature term high, meaning, you are forcing the network not to make highly confident decisions in the first run of feed forward step, right? So it's more spread out. And now if the feedback is saying, it enhances a certain class, then you can over time, right, reduce the temperature term and anneal and slowly become more confident.
I see. So just thinking out a bit loud over here. So can this notion be incorporated once the model has been trained, even like let's say the concept we were discussing earlier with the denoising, and when you have these nodes and it gives some sort of feedback. Now let's say if I want to extend it to a new concept that's coming in, how, like I'll go back to my running example. If I know all about the cats and now there's a dog example coming in, first, if I know that, okay, if this kind of data distribution, if this kind of dog example has never been seen, and let's say if I just use this notion of self-consistency, which you nicely put up, and now in the self-consistency, I say that given a data distribution, I learn some projection operator, which tells me, okay, this is the space. Say an autoencoder by which is doing just the reconstruction. And if it's not able to reconstruct the dog example, maybe it has not seen that, that data distribution. If I use that as a new notion and define a threshold over there, can I not be able to incorporate this new example coming to my already learned model? Am I making sense?
Right. No, exactly. I mean, as I said, right, that's lifelong learning. I mean, in principle, right, you should be able to do it. The question is how well can it figure out entirely new concepts, right, that are big distribution shift from the known distribution. That's something to be tested.
Right.
I mean, it's going to be challenging, right? But in principle, you need something like this to, I mean, can at least assess out of distribution, which we did that as a quick study, like it's able to assess that well. The question is, from there to learning new concepts is a big leap, right? From detecting.
Right. So one of the things which I am exploring in my work currently is, now it's very challenging if you have a, let's say, a fixed model, but what if you introduce a new model? So instead of saying that one model incorporate a new concept, but rather say that there is a model for a concept. So you have a dictionary of the models. So in that case, you look through the different models, like let's say using simple self-consistency. So model one, check it does it contain or not. So on, you check on different MN models, and then let's say if you are satisfied that it is not something that you have seen in any of your existing models, then you can incorporate a new model. That makes life easier because then you don't have to touch the existing concepts. You just say that I'm going to add a new concept in my dictionary. It's like I think I may be wrong over here, but it's like the way we humans sort of learn these new things. We add a new list of tasks implicitly whenever there might be certain things which might have less correlation, but when it comes in, we just add new models or new tasks in our list.
I mean, I think the thing is, we are able to face an infinite vocabulary, right?
Yeah.
But the kind of this approach would be limited by how much you can store. And it doesn't have compositionality. I think the other aspect is how to build in this compositionality, because, dog is still related to cat in so many ways, right? You don't want to just create a new one. I feel like that would be limiting how many new concepts you can learn, and also share the learning you've already done with other concepts.
Right.
But it's a good first step.
Yeah. Is there anyone who wants to ask a question? I think we are already over time, so we'll not hold Anima more. Anyone? Maybe last chance? Okay, if not, then let us thank our speaker. Thank you, Anima.
Thank you. Great. And if people want to reach out to me if they have other questions, please do. Thank you.
I will do that. Thank you.
Take care, everyone.